Hi everyone, Dr. Crahay here. In this lecture we're going to be talking about Chapter 6, so normal distribution, standard normal distribution, and z-scores, and we'll do some work finding the proportion under the curve, so the area under the curve. So first things first, I do have my new technology, so if this is still hard for you to see, hard for you to hear, please do let me know, and I'll do some extra work to figure out how to make this better for you. Now, in the behavioral sciences, we know that as you collect more and more data, this will start to approximate a normal curve. We'll come back to that picture in just a second. A normal curve, a normal distribution, sometimes it's called a Gaussian distribution. It's called all sorts of different things, but what is it? Let's go back to our days of drawing frequencies, right? So remember, we would have our x here, and then we would plot the frequency up here. So I think we talked about IQ a couple of times. So maybe we had an IQ of 100 there, 200 here. I'm not sure if it goes down to 0, but we'll put a 0 there. And then we said, okay, person A was down here, person B, person C, person D was right here, the next person here, next person here. And so we were making these kinds of histograms based on the frequency of scores. Well, as you collect more data, they start to take a certain shape, and that is a normal curve. Something kind of like that. Again, I'm a really horrible drawer, so it's not that great. But this is approximately a normal distribution. So it'll look something like this bell shape. There are a couple of things you'll notice. So in this area right here, this area right here, they do not touch. So it's asymptotic. They won't touch there. They are symmetrical, so you should be able to draw a line right down the middle there. So see here, I didn't do a great job. And 50% will be below, 50% above. You could fold this in half, and they should be exactly equal. I think I did a better job with this one there. So behavior approximates a normal distribution as we get increasing observations. Other things we need to know: 100% of our data will fall under this curve. So 100% of the data will fall in this purple shaded area that I'm doing for you up here towards the top right. All of our data will fall under this curve with a normal distribution. Because of that, and because we know that this is symmetrical, we know a couple of things. 50% will be below, 50% will be above. In fact, we can slice these up, and I can tell you exactly what proportion of the data is in this section, for example. I could also look at the data in this section over here, and I could tell you, okay, is this part bigger or is this part bigger? So that's a lot of what we'll be doing in our homework this week. We also know the location of the mean, median, and the mode. So we have a normal distribution here, so probably a large number of participants in this data set. We know that it is symmetrical, half fall below, half fall above, so hopefully you are already seeing where I'm going. Our mean is right here in the center. Our median is also going to be right there in the center. Our mode should also fall all right there in that center. In this top right one, they would all be where I've drawn this little bar here. So our mean, median, mode will be the same in a normal distribution. It will be located in the very center, and then we can splice it up in a couple of different ways. Now, knowing that, what is all of this business about a standard normal? So let me write that real quick. Standard normal. What are we talking about here? It's the same thing. Still our normal distribution. But instead of raw scores down here, we're going to put what are z-scores. So if we scroll up here, these are all raw scores. So you can get a 100 on an intelligence test, that's a raw score. Down here, we're going to put our z-scores. So it's really just a way to convert our raw scores into a standardized form. So it's just getting into a standard form so that we can really compare across variables. So this is kind of the comparing apples and oranges kind of a situation. It's so that we can just turn everything into an apple and compare it against each other, right? So there are a couple of things here that I want to point out about the standard normal distribution before I tell you about calculating z-scores. First things first, we still know 100% of the data will fall under this curve. These will still not touch there at the ends. Let me cancel that out. Sorry, still learning technology. 100% of the data falls under this. These will not touch. It is still symmetrical. We can still draw a line right down the middle there, and we know 50% below, 50% above. The only thing that changes are these numbers that we put down here. So earlier I put 100, 200 at the top, 0 down here. Let's go ahead and draw a couple of lines here so I can really show you some of this. Now this would be 100 minus 15, and I'll tell you more about that in a second, but that should be 85. That would make this there. 115 would be this line. 130 would be this line. Hopefully I've done this math correctly. Now, these are raw scores. Those are your raw scores. Now, z-scores are a tiny bit different, so what it's going to do, your mean is going to be 0 every single time. Standard deviation will be 1, which means this is 1 standard deviation, 2 standard deviations. We have -1, -2. If we had another, we would go down to -3. So what a z-score does is it takes the raw score and then converts it to a standardized form so we can compare across different units of measurement. So where the raw score here is 100, its z-score would be 0. So this is what's called a z-distribution. Now, how do we calculate a z-score? What the heck is going on here? Well, actually, let's make that a little bit lighter. Population. So we still have this population versus sample distinction, right? So the population, again, would be every single person that you're interested in the entire United States, in the entire world, whatever you're interested in. It's going to be a really large number that you can probably never really obtain, but this is your z. So it's your raw score minus your population mean over your population standard deviation. That is your z-score. Now, well, what about for a sample? So we use samples quite a bit more. Z-score, it's going to be the same thing, your raw score minus your mean. So again, I'm using x bar divided by your standard deviation. So these are exactly the same thing. Raw score minus your mean. Here it's your population mean. Here it's your sample mean. Divided by your standard deviation, population standard deviation, sample standard deviation. Now for IQ tests, we know, it's been a while, this may have changed, but last time I checked, we know that the mean is 100, the standard deviation is 15. So if we wanted to say, okay, with a raw score, so I'm going to do that with x, you could see it xi, so someone asked about that in the questions last week, so I'm going to make sure and include that here. Xi, it could be, sometimes people will do x sub 1, sub 2, sub 3. It's just x for an individual, so for one person. With an x of a raw score of 100, what is my z-score? So let's calculate that down here. So let's say we're working with a sample. Sorry, I keep pushing some buttons here. So we know z equals x minus x bar over the standard deviation. Our raw score, I've just given it to you, is 100. our mean is also 100 over the standard deviation is 15. So we know this works out to be 0 over 15, so we know that z-score is going to be 0. Look right here. So raw score of 100, our z-score is 0. So pretty straightforward for that one. We'll just do another straightforward one. We'll do some more complicated ones in the homework and in the application video coming up. But what if we have a raw score of 130? So it should be a z of 2. I'm going to put little things on my z's there so that we can tell what I'm talking about. So our raw score again is 130, so we're going to take 130 minus our mean. We look up here, the mean's 100, divided by the standard deviation's 15. 130 minus 100 gives us 30 over 15. Our z is in fact 2. So z equals 2 there. So that's kind of the straightforward way to do this. And that is the basics of the standard normal distribution, the z distribution. So we know it lines up perfectly with a normal distribution here. Raw scores. This is how we would look at it with a normal distribution with raw scores of 0, 70, 85, 100, and so on and so forth. If we want to convert those to z-scores, we'll be looking at -2, -1, 0, 1, 2. We still know, though, 50% of the scores fall up here. We know the percentage that are right here, so I'll show you that right now. So remember, this is symmetrical, so we know, thanks to the empirical rule, what these different proportions are. So we can actually see here 34% fall between the mean and 1 standard deviation. So 34%, let me get a different color here, 34% of the data fall between the mean, which is right here, and 1 standard deviation. 34% of the data are right here. Well, guess what? 34% of the data are also right here. So here's where you can see how horrible my drawing is, because this looks so much bigger. This is 34%. I'm going to lose that pink color. This is also 34%. So because of this empirical rule, we know 34% are here, 13.5 will be in these, 2.4 at the end. So we can tell, given a particular z-score, where they fall, how many people scored lower than them, how many people scored higher. We can tell what proportion of scores are between 85 and 115, which by the way, the answer is 64, because we know 34 right here, 34 right here. So we can start to locate where these scores are. To do that, we need a z-table. So there is an abbreviated z-table. Get some fresh paper here. So page 174 has an abbreviated z-table, or you can also find the full deal on page 655. If you're interested, you can find those proportions, and actually you'll need them for your homework as well. I have a version right here that I'll show you. Oh, I can't draw on this. One thing that you need to pay attention to when you're looking at these normal tables is what they're telling you. So this says table entry for z is the area under the standard normal curve to the left of z. So you've got the z-score here to the tenths place, and then you go out to the hundreds along the top. So if we had a score 3.11, 3.1 and then 1 would be this right here. So we know to the left of negative 3.11 there's 0.0009% of the data. So let me go back to my drawing and show you what that is telling us. So we have our normal distribution. So we've got 0 here, right? So z, 0, -1, -2, -3. So that was telling us -3.11 is probably going to be right here. The area to the left of z, which is this pink area, I've already forgotten what the number is though, 0.009. 0.00, yep, I missed a 0 there, 0.000, so let me squeeze a 0 in right here. 9% of the data falls to the left of 0.311. We also have, here's a 1, here's a 2, here's a 3. So what if we want to know what proportion of the data fall to the right? Let me get a different color. To the right of z equals 1. So you're going to have a couple of these homeworks, and we're going to work through them in the next video, but when it's asking you questions, I recommend drawing this picture, right? So we want to know what is to the right of z equals 1. So find z equals 1, color the direction that you want, and now what we'll do is we'll go into our table, look at z equals 1, and find that proportion. So this table is giving us to the left of z. This is also to the left of z, so we are looking for, what did I say? z 1.00, sorry, pulling up the wrong thing here. So we find our z 1.00 is going to be right here, 0.8413. 0.8413. But remember, that was telling us to the left. So with that number in this particular table, and you have to pay attention to what the table is telling you, because they are all different, that is telling us this part right here. 0.8413 or 84.13%. Same thing. So I told you that the area under the curve is 100%, or it is 1.000. So an easy way to do this would just be to take 1 minus 0.8413, or 100 minus 84.13. So let's pull out the calculator. 1.00 minus 0.8413, so 0.1587, or 15.87% is in this blue area. So 84% to the left, about 15% to the right. So we'll have a lot more practice locating proportions under the curve. This is the kind of basic introduction stuff to it. Again, as you're going through these and it's asking you these questions, make sure that you draw these pictures and really color out, because otherwise there are a lot of silly mistakes to be made. I make them all the time, and that's why I started drawing these. So we have talked about the normal distribution. We know behavior starts to approximate this as you get larger and larger sample sizes. We have the standard normal distribution, which is the same thing, but we just convert it to a standardized form so that we can compare. We know the exact proportions under this curve. We know that they are symmetrical, so you can divide it right down the middle, 50% below, 50% above. We can break this down into the teeniest, tiniest fractions and know exactly what proportion is to the left of a z-score, what proportion is to the right of the z-score, and there are actually pages and pages of tables giving us these numbers so that we don't have to do those hand calculations of that. We know how to transfer, how to calculate, so population and sample z-scores. Again, in this class, mostly we'll be using the sample z-scores, unless it says in the instructions to use the population. We'll be using the sample. So you just take the raw score, subtract the mean, divide by the standard deviation, and then that opens the door to figure out all of these different proportions. Okay, in the next video, I'm going to work through portions of your homework, and I'll pause for some questions there so that you can do this on your own and test your work before you turn it in to me. So if you have any questions while you're going through that, let me know, but definitely make sure to watch that. I recommend watching that before you do your homework, and find those errors that you're making and make those corrections before doing the full thing.